So this is a problem-solving question that has some interesting aspects worth exploring. What we're told is a 12 centimeter long thin rod has the non-uniform charge density, and they give you an equation here for lambda, which is our charge density. And it's in terms of x, because we've got this long object, so the charge density is varying in x. And we're also told that x is measured from the center of the rod. And then we're asked, well, what's the total charge? Okay, so why did they tell us that x is measured from the center of the rod? Well, that's kind of interesting. And if we look, so I've drawn out the rod. So here's our rod. And we are told that it's 12 centimeters long. But we're thinking about it in terms of with respect to the middle. So I've drawn it from -6 centimeters to +6 centimeters. But we've got a total length of 12. So why are we thinking about this from the middle? Well, let's look at the equation. So our charge density is, well, this is just a number. So that's just a number times an exponential function. So right away we know that in x there is going to be an interesting decline. Okay, so it's an absolute value of x over 6. So what does that mean? Well, that means that there's going to be an interesting symmetry on both sides. So on the side of positive x and the negative x direction. In fact, they're going to look like mirror images of one another. The first thing that we could decide to do when trying to understand, well, what does this equation mean? Just kind of looking at it. Well, we could try to substitute in a few values and just kind of get a feel for what this is going to look like. The obvious place to start when trying to understand an equation is often going to be, well, what about it x is equal to 0? And in this case, that's right in the middle of the rod. Now, you don't need to do this to solve the question, but I thought I'd kind of explore it a little bit so we understand, when you look at an equation, what you might do to unpack the scenario and understand a little bit better the strategy we're going to employ for working through the math. Okay, so what's lambda at x is equal to 0? Well, if x is equal to 0, then e to the 0 is 1. So this becomes 1, and we're left just with 2. So right in the middle, the answer is 2 nanocoulombs per centimeter. Okay. That wasn't so bad. So then we could say, well, what about lambda where x is equal to infinity? Way, way out there. I mean, not at 6 centimeters. I mean, what does the function do way out there? Well, if x here is infinitely large, well, this is actually going to be 1 over, e to the infinity, because this is negative x. So we're looking at 1 over infinity. And 2 divided by infinity is going to be 0. Basically, we just get to 0. And so there we go. And we may suspect that basically we've got a maximum charge density in the middle, and that's dropping off exponentially. And eventually that exponential approaches 0. If we really wanted to convince ourselves a little bit more, what could we do? Well, the next logical one in context is to say, well, what about x is equal to 6? What's happening there? Well, we've got 2 nanocoulombs per centimeter, and then e to the negative 6 over 6, so that's e to the negative 1. Okay, well, that means just 2 divided by e, and e is just a number, so that's 2.7, etc. It's a long number, a rational number. So this works out to 0.7 nanocoulombs per centimeter. Okay, so now we've got actually some pretty good points, but I just want to add maybe one more so that we can kind of fill this out, because it's an exponential function, so it's not as easy to plot as if it was linear. So let's get a feel for that by adding one more, and that's going to be, I want to know, in order to plot this out pretty well, I want to know, well, what about when lambda at x is equal to 1? Because basically, if we want to plot these things out, what do we know already? And I've got a little axes here. Well, we know that at x is equal to 0, right there along the lambda axis. Well, we know that the value is 2. And we know that really far away it goes to 0. But we also know that at x is equal to 6, which is there, then it's at 0.74. So that's, let's say it's about here. It's about there. Okay. Well, now we don't have enough. We need like one more point at least to get a decent approximation for what this function is doing. So what about lambda is equal to 1? Well, that should be somewhere in between here, right? Because that's right here. And that I'm choosing as well. It's a convenient value for the math of it. Okay. So the lambda is equal to 1. Well, that means equal to 2 nanocoulombs per centimeter, and then e to the and we'll just say that the negative x, we're going to look at the positive side, so the negative x over 6 centimeters. I've kind of lost the 0.0 on these numbers just to be a bit more compact. Okay, and so here what I'm doing is, well, now I got to solve for x. So that's not a big deal. What I'll do is I'm going to take the 2 nanocoulombs and divide that out. That'll be the first thing I do. So I have 1/2, a little bit more room, 1/2 is equal to e to the negative x over 6. And then to get things out of that exponential, then I'm going to do ln of both sides. Because when you do ln of both sides for this type of function, what you do is you can now get that term out front. So we get negative x divided by 6 centimeters out front of ln e, and then ln 1/2. Okay, well this is great because the ln e is 1, so that disappears. And just kind of make a note of that. And then what we're left with is ln 1/2 is equal to x divided by negative x divided by 6 centimeters. So we'll rearrange for x. And so we have x is equal to minus 6 centimeters. It's really 6.0 centimeters times ln 1/2. And that's just a number. You can do it in your calculator. And so x is equal to 4.2 centimeters. So that was a little bit of work, but it's not so bad. It's just our exponential rules at play. So x is equal to when, just reminding myself when lambda is equal to 1. Okay, so now we've got one more point here, and we can say, well, lambda is equal to 1, x is equal to just past 4. So something like this. So now we get a sense that, well, this is some steady. It's not so easy. It's not so easy to draw a smoothly varying, and it'd be kind of like this. And what we know from the equation is that this will happen the exact same way on the other side. So that's just on the positive side. It's just going to happen identically over on the negative side. So we were at negative 6. That's going to be negative 0.74, and then at 1, this is going to be like that. So it's going to hopefully look sort of symmetric, and so it does. And what I've done actually ahead of time, because I wanted to give you a nice view of this function. So I've gone ahead and plotted this in Python. So here's a nice version, and you know what? It's not too bad compared to what we drew out there. So you see that we got a really good sense of things. So if we do like a really much better job, and we have a computer fill it in, then this is what we get for our density. Okay, so that's great, but what about our original purpose here? What were we doing? Well, we were saying that we wanted to know, let's go back to the top, what is the total charge? Well, what we know is that if you want to know the charge, if you want to know the charge on some extended object, well, you just integrate all the little DQs. You could divide an extended object up into little pieces, tiny pieces, and then you add them all up, and that's what an integration is. And then we could say, well, I'm just going to bring this down to the next page. And so really what we're doing is we're going to say, well, what is a DQ in this case? Well, a DQ is going to be our lambda x dx. So this is our density, our charge density. Remember, so this is coulombs per meter, and this is going to be our meters, so we end up with coulombs, if you want to take a look at the units there. Okay, so then we have an integration of lambda x dx is going to give us our q. And we already know what our lambda x function is, so we're going to go q is equal to the integration of 2 nanocoulombs per centimeter times e to the negative absolute value of x, 6 centimeters. And I'm again omitting the 0.0 just because it makes it easier to kind of write out here. Okay, so we're integrating this area under the curve, and we can't do that graphically because it's an interesting curve. Okay, so let's take a look at what we've got now. Now in our case, what we're doing is we're integrating across an object, this rod, back up here. We're going to go from one side to the other side. But of course, there's a nice symmetry that we can take advantage of in that things are the same on both sides. So what we could do is just say, well, let's look at this, let's get this, and then we'll just multiply it by 2. And so that's how we're going to set up this integration and why we're going to set it up in that way. So now let's take a look at what this looks like. We're going to integrate from 0 to 6 centimeters. And we're going to integrate from 0 to 6. And we've got this equation, 2.0 nanocoulombs per centimeter e to the negative x, okay, divided by 6 centimeters. The absolute value was describing the fact that we have this pattern on both sides. We're only looking here at the positive. So we're just looking at the positive part of this. And then we're going to multiply the whole thing by 2. Okay, so now we've set all this up. And I just want to make a note for why we did that. So if somebody just reads this, they can follow along. So we're going to drop the absolute value of x and replace it with x. And we're going to gain a factor of 2 because we will integrate only the positive half, since both halves are symmetric. That's our little note for that step, because that's important. The symmetries gives us a way to make this a bit easier on ourselves, provided we see that and follow through. So we can actually take, the first thing I want to do is, well, the first thing I always want to do with an integration or a derivative, I just want to take things out that don't need to be there. So we're going to take this constant value out front. So then we end up with 4.0 nanocoulomb per centimeter. And then, okay, now we've got our integral from 0 to 6 centimeters, exponential to the negative x. Oh, yeah, so I forgot all along a dx. It's important that we keep the dx. Okay, 6 centimeters dx. Okay, and that's all for q. So now what are we doing? We are integrating an exponential term. Okay, how do we do that? Now we're into more of a math question. Well, you can recognize that this follows a standard integral, which is the integration of some e to the ax. And a is, whatever, and that's equal to 1 over a e to the ax. And most physics textbooks actually have a table of common integrals because they come up all the time. And if you don't remember the pattern, then you can just look it up. That's the scientist's approach. Okay, and so in our case, so if a is equal to, what's a in our case? Well, a in our case is negative 1 over 6. So following this pattern, if a is equal to 1 over 6, then the integral of e to the x negative 6 is going to be equal to negative 6 e to the negative x over 6. Okay, so that's applying our integral pattern to our particular situation. Okay, so let's come back over here and we'll do 4 nanocoulombs per centimeter. That's still hanging out front. And then we're going to say, well, what does our integral end up being? Well, it's going to be a term of negative 6 centimeters and then e to the negative x over 6 centimeters. And that is going to be evaluated at 0 and 6 centimeters. All right, so our charge is now going to be, well, I'm going to pull out the 6th term. I'm going to kind of bring that out, and we're going to have 4 nanocoulomb per centimeter. I'm going to pull out this negative 6 centimeters. And we see where the units are going there. The centimeters will cancel, and we'll end up with a charge, which is what we want. That's excellent. And just so I'm not crowded, I'm going to bring this down just a wee bit. Okay. And so then here we've got e to the negative x over 6. Evaluate at 0 to 6 centimeters. And at that point, okay, so we're going to say that the charge is equal to, we've got 4 times negative 6. So we end up with negative 24 nanocoulombs. And then we're going to first evaluate, we've got e to the negative 1, and then subtract e to the 0. remembering that we can then e to the 0 is 1. So that's 1. Okay. So now what do we have? Well, we've got negative 24 nanocoulombs, 1 over E minus 1. And so we end up, if you round this to 2 significant digits, then you end up getting 15 nanocoulombs. Okay, so there we are. That's how much charge you've got if you integrate the given function. That is represented by, we can do a nice plot, we can do a rough plot, and it gets you to the same place. Okay, that's it.